Tonight, we're going to explore something that will completely reshape how you picture our place in the galaxy. You've probably seen those diagrams of the Milky Way, the ones that show our sun sitting in a tiny little spur between two massive spiral arms. The Orion Arm. It looks small. It looks like almost nothing. A minor feature on a galactic map, barely worth labeling. But here's what those diagrams never tell you. That tiny spur, that small, insignificant-looking sliver of the galaxy that we call home, is so enormous that if you could travel at the speed of light, it would still take you thousands of years to cross it. The Orion Arm isn't small. It only looks small because the galaxy is incomprehensibly large. And tonight, you're going to understand exactly why that matters. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with where we actually are. Not on Earth, not in the solar system. Those scales are too small for what we're talking about tonight. Let's start with the galaxy, the Milky Way. You've heard the name 1,000 times. You've seen pictures of it, or at least artist impressions of it, because no human has ever seen the Milky Way from the outside. Every image you've ever seen of our galaxy as a whole is an illustration, a reconstruction based on observations we've made from the inside. We are inside this structure. We're embedded within it. And that makes understanding its shape and layout enormously difficult. It's like trying to draw a map of an entire city while standing in the middle of one room in one building. You can look out the windows, you can see other buildings in the distance, you can measure how far away certain landmarks are, but you can never step outside and look down from above to see the whole thing at once. That's essentially what astronomers have been doing for centuries, piecing together the structure of the Milky Way from the inside, using careful measurements and observations to figure out the shape of the galaxy we live in, without ever being able to leave it and look back. What we figured out is remarkable. The Milky Way is a barred spiral galaxy. That's a specific type of galaxy with a well-defined structure. At the center sits a dense concentration of old stars called the Galactic bulge. This bulge is roughly 10,000 light-years across. It's packed with stars, far more densely than our region of the galaxy. If you lived on a planet near the galactic center, your night sky would be blazing with thousands of visible stars, many of them bright enough to cast shadows. The sky would never truly get dark. Running through the center of this bulge is a bar. Not a bar you'd walk into, but a bar-shaped structure made of stars. Imagine a thick beam of starlight running through the heart of the galaxy. This central bar is estimated to be roughly 27,000 light-years long, though exact measurements vary depending on which study you read and which method was used. The bar is made up of older, redder stars. It's a prominent feature that helps define the Milky Way's type. Not all spiral galaxies have bars. Some do, some don't. Ours does, which puts it in the category of barred spirals. Extending outward from the ends of this bar are the spiral arms. These are the features that give spiral galaxies their iconic appearance. When you see photographs of other spiral galaxies, the ones taken by the Hubble Space Telescope or the James Webb Space Telescope, showing beautiful face-on spirals with sweeping curving arms of blue and white light. Those arms are what we're talking about. The Milky Way has them too. We just can't see them from the outside. Now, here's something important to understand about spiral arms because most people get this wrong. Spiral arms are not solid structures. They're not walls of stars or rivers of matter flowing around the galaxy. If they were, they would have wound themselves up and disappeared billions of years ago, because the inner parts of the galaxy rotate faster than the outer parts. A solid arm would get twisted tighter and tighter with each rotation until it wrapped around itself and vanished. But spiral arms have persisted for billions of years. The reason is that spiral arms are density waves. Think of them like traffic jams on a highway. If you've ever been on a road where traffic suddenly slows down for no apparent reason and then speeds back up, you've experienced a density wave. The cars themselves aren't stuck in one place. They're moving through the slow zone, but the slow zone itself stays roughly in the same location. Cars enter it from behind, slow down, and then speed up again as they exit. The jam persists even though no individual car stays in it for long. Spiral arms work the same way. Stars and gas clouds orbit the galactic center at different speeds, depending on their distance from the center. As they move through the galaxy, they encounter regions where the gravitational field creates a compression. This compression is the spiral arm. Gas clouds entering this region get squeezed, which triggers star formation. New stars light up inside the arm, especially hot blue stars that burn bright and die young. These bright young stars are what makes spiral arms visible. They're like neon signs marking the location of the density wave. The stars eventually move out of the arm and continue their orbits, but new stars keep forming inside the arm, keeping it visible. This is why spiral arms appear blue and bright in photographs of other galaxies. They're full of young, hot, newly formed stars. The spaces between the arms contain older, redder stars that have already passed through. The arms aren't places where all the stars are. They're places where the newest, brightest stars are being born. The Milky Way has several major spiral arms. These are the large-scale features that define the galaxy's structure. The names might sound unfamiliar because they're named after constellations in whose direction we observe them from Earth, but they're some of the largest structures in the entire galaxy. The Perseus Arm is one of the two major arms. It lies outward from the Sun's position, farther from the galactic center. If you could somehow hover above the Milky Way and look down, the Perseus Arm would be one of the most prominent features you'd see. It's a long, sweeping curve of gas clouds, star-forming regions, and bright young stars stretching for tens of thousands of light years around a significant portion of the galaxy. Inward from the Sun's position, closer to the galactic center, lies the Sagittarius-Carina Arm. This is the other major arm in our general region of the galaxy. When you look toward the constellation Sagittarius on a clear night, you're looking roughly toward the galactic center, and the Sagittarius Arm is one of the structures between us and that center. Then there's the Scutum Centaurus Arm, which is one of the most massive features in the entire Milky Way. This arm wraps around a huge portion of the galaxy, extending from the far end of the central bar and sweeping outward in a grand spiral. It contains some of the most active star-forming regions in the galaxy. Some studies suggest it's the richest and most prominent arm in the Milky Way. There's also the Norma Arm, located closer to the galactic center, and the Outer Arm, which lies beyond the Perseus Arm in the galaxy's outer regions. The exact number and arrangement of the Milky Way's arms has been debated for decades. Some models show 2 major arms, others show 4. The difficulty of mapping something you're inside of means that our picture of the Milky Way's structure has changed over time and continues to be refined with the new data. But the general picture is clear. The Milky Way has several large spiral arms that wrap around the galaxy like the arms of a vast pinwheel, each one stretching for tens of thousands of light years, containing billions of stars and enormous clouds of gas and dust where new stars are constantly being born. Now, here's where we get to the part that matters most for tonight's story. Between these major arms, there are smaller features. Think of them as branches or spurs that connect the larger arms, or extend outward from them like smaller streams feeding into a river system. These smaller features are not as long or as prominent as the major arms, but they're real physical structures containing real stars and real gas clouds. And one of these smaller features is the one we live in. It's called the Orion Arm. You'll also hear it called the Orion Spur, the Orion Cygnus Arm, or the Local Arm. The different names reflect the fact that astronomers have been debating its exact nature for decades. Is it a full arm? A spur? A bridge between 2 larger arms? The answer has shifted over time as our measurements have improved. But the traditional view, the one you'll find in most textbooks and diagrams, is that the Orion Arm is a minor structure. A spur, a small feature sitting between the much larger Sagittarius-Carina Arm on the inside and the Perseus Arm on the outside. On those top-down diagrams of the Milky Way, the ones you see in textbooks and documentaries and websites, the Orion Arm is usually drawn as a short segment, a small bridge, sometimes barely labelled. The major arms sweep grandly around the galaxy in bold colours, and then there's our little spur, tucked between them like an afterthought. The sun is marked with a tiny dot somewhere along this spur, and you look at it and think, well, we're in a pretty insignificant part of the galaxy. We're not in one of the major arms, we're in a spur, a minor feature, something small. And that impression, that feeling of insignificance, is what those diagrams create, but that impression is deeply misleading. Because even though the Orion Arm is classified as a minor feature of the Milky Way, a spur rather than a major arm, its actual physical size is staggering. We're going to get into the exact dimensions soon, but for now, understand this. The Orion Arm contains billions of stars. It spans thousands of light years. It includes some of the most famous and spectacular objects in the night sky. It is a structure so vast that the entire history of human space exploration hasn't even scratched the surface of exploring it. It only looks small because the things next to it on those diagrams are even more unimaginably large. The problem isn't that the Orion Arm is small. The problem is that our sense of scale completely collapses when we try to comprehend anything at galactic dimensions. Our sun sits within this structure. Specifically, the sun is located roughly in the inner edge of the Orion Arm, slightly closer to the Sagittarius Carina Arm side than the Perseus Arm side. We're about 26,000 light years from the galactic center. That number deserves a moment of reflection. 26,000 light years. Light, which travels at about 300,000 kilometers per second, the fastest speed possible in the universe, would need 26,000 years to travel from where we are to the center of the galaxy. When you look in the direction of the constellation Sagittarius on a summer night, you're looking roughly toward the galactic center. But you can't see it with your eyes. The galactic center is hidden behind vast clouds of dust and gas that block visible light. We can only observe it using infrared light and radio waves, which can pass through the dust. The light you'd see from the galactic center, if the dust weren't in the way, would have left there 26,000 years ago. That's long before agriculture was invented, long before any city existed, long before writing, before pottery, before any of the things we associate with civilization. When that light began its journey, humans were living as hunter-gatherers in the last ice age, using stone tools and following animal herds across landscapes that were covered in glaciers. That's how far we are from the center of our own galaxy. From our position in the Orion Arm, we orbit the galactic center along with every other star in the galaxy. The sun moves at about 230 kilometers per second around the galactic center. That's an incredible speed. At 230 kilometers per second, you could cross the entire United States in about 3 minutes. You could circle the Earth in under 3 minutes. And yet, even at this phenomenal speed, it takes the sun approximately 225 million to 250 million years to complete one single orbit around the galaxy. One galactic year. The last time the sun was roughly where it is now in its orbit, dinosaurs were just beginning to appear on Earth. The time before that, complex multicellular life was only just starting to diversify after the Cambrian explosion. Earth has existed for about 20 galactic years. The entire age of our planet can be measured in a handful of laps around the galaxy. And during all that time, the sun has been moving through the galaxy, sometimes inside a spiral arm, sometimes between arms, always part of this vast rotating structure. The sun's position in the Orion Arm isn't permanent either. Over millions of years, the sun drifts relative to the spiral pattern. Remember, spiral arms are density waves, not fixed structures. Stars move through them. The sun has probably passed through multiple spiral arm regions over its 4.5 billion year lifetime. Right now, we happen to be in the Orion Arm. Millions of years ago, we might have been between arms. Millions of years from now, we might be approaching the Perseus Arm. The galaxy is dynamic. Everything is in motion. But for now, for the slice of cosmic time that includes all of human history and all of human existence, we are residents of the Orion Arm. Understanding where we sit in the galaxy is crucial for what comes next. Because the structure of the Milky Way, the arrangement of its arms and spurs and interarm regions, isn't just an abstract map. It has real physical consequences. The spiral arms are where most star formation happens. They're where the gas is densest, where molecular clouds collapse under their own gravity to birth new stars. They're also where the most massive and short-lived stars exist, the ones that explode as supernovae at the end of their brief lives. Living inside a major spiral arm would mean being surrounded by more stellar activity, more radiation, more supernova, and potentially more danger to any life trying to develop on a planet nearby. The fact that we're in a minor spur rather than a major arm might actually be significant for our existence. The Orion Arm is quieter than the Perseus or Scutum Centaurus arms. There's less intense star formation, fewer massive stars exploding, less disruptive radiation. Our position in a relatively calm part of the galaxy may have given Earth the stability it needed for life to develop and persist over billions of years. This idea is sometimes discussed under the concept of the galactic habitable zone. The idea that there are regions of the galaxy that are more favorable for life than others. Too close to the galactic center, and the density of stars and supernovae creates a hostile environment. Too far out, and there aren't enough heavy elements forged in stellar explosions to build rocky planets like Earth. The Orion Arm, sitting roughly in the middle distance from the center, in a relatively quiet spur, might be something of a sweet spot. Not too active, not too sparse, just enough stellar chemistry to produce planets with the ingredients for life, but not so much violent activity that life gets wiped out before it can take hold. This is the landscape we inhabit. A barred spiral galaxy 100,000 light years across, containing somewhere between 100 billion and 400 billion stars, structured into sweeping major arms and smaller connecting spurs, all of it rotating around a central, supermassive black hole called Sagittarius A star, which has a mass of about 4 million times the mass of our Sun. And within all of that, we are here, in the Orion Arm, a minor spur in the grand scheme of galactic architecture, positioned about 26,000 light years from the galactic center, orbiting at 230 kilometers per second, but still taking 250 million years to make it around once. Surrounded by billions of stars that are our neighbors in this structure, yet separated from even the nearest of them by light years of empty space, this is our address in the cosmos, not Earth, not the solar system. Those are just the room and the building. The Orion Arm is the neighborhood. And as we're about to discover, that neighborhood is far larger than any diagram has ever made it look. The flat images, the simplified maps, the neat little labels drawn on posters and projected in planetariums, they all commit the same sin. They compress scale. They take something that spans thousands of light years and reduce it to a centimeter on a page. And in doing so, they strip away the very thing that makes it astonishing. Its size. Every time you've glanced at one of those galaxy diagrams and thought the Orion Arm looked small, your brain was being tricked. Not by any deliberate deception, but by the sheer impossibility of representing galactic scale on a human-sized image. You were looking at something vast and reading it as something minor. And that misreading, that failure of intuition, is exactly what we're going to correct as this journey continues. Because the Orion Arm isn't a footnote in the galaxy's structure. It's a colossal region of space containing more distance, more stars, and more worlds than humanity could explore in 1,000,000 lifetimes. It just happens to sit next to things that are even more colossal. And that difference between being small and merely being smaller than something else is the entire point of what we're exploring tonight. The Orion Arm is not small. The galaxy is just that incomprehensibly large. So let's talk about actual numbers. Let's put real dimensions on this structure that diagrams have conditioned us to dismiss. Because once you see the true measurements of the Orion Arm, once you actually process what those numbers mean in physical terms, you will never look at a galaxy diagram the same way again. The Orion Arm is estimated to be roughly 10,000 light years in length. Some studies put it slightly shorter, others slightly longer, and recent data from the Gaia spacecraft has suggested it may extend even farther than traditional estimates. But 10,000 light years is a solid working number based on decades of radio observations, parallax measurements, and surveys of young stellar populations and hydrogen gas clouds within the structure. Its width is roughly 3,000 to 3,500 light years. So we're talking about a structure that's approximately 10,000 light years long and 3,500 light years wide. Those are the dimensions. And I want to make sure you actually understand what those numbers mean, because it's very easy to hear a number like 10,000 light years and just file it away as big without truly grasping the scale involved. 1 light year is about 9.46 trillion kilometers. That's the distance light travels in a single year, moving at about 300,000 kilometers per second. Every second, light covers 300,000 kilometers. Every minute, it covers about 18 million kilometers. Every hour, over 1 billion kilometers. Every day, roughly 26 billion kilometers. And after a full year of traveling at that speed, non-stop, never slowing down, light has covered about 9.46 trillion kilometers. That's 1 light year. Now, the nearest star to our sun, Proxima Centauri, is about 4.24 light years away. That's the closest star, the very nearest neighbor we have. And it would take light, the fastest thing in the universe, over 4 years to get there. If we sent the fastest spacecraft humanity has ever built, the Parker Solar Probe at its peak speed of about 192 kilometers per second, it would take roughly 6,800 years to reach Proxima Centauri. That's longer than all of recorded human history. Writing was invented about 5,000 years ago. If we had launched a spacecraft toward Proxima Centauri the day humans first learned to write, it still wouldn't have arrived yet. That's just 4.24 light years. The Orion Arm is 10,000 light years long. 10,000. Not 4. 10,000. If 4 light years is already a distance so vast that no human technology could cross it in less than thousands of years, then 10,000 light years is something that simply refuses to fit into the human mind. Let me try to break it down another way. If you could somehow travel at the speed of light, which you cannot because nothing with mass can reach that speed, but if you could, it would take you 10,000 years to travel from one end of the Orion Arm to the other. 10,000 years. Let's put that in a historical context. 10,000 years ago, humans were just beginning to experiment with agriculture. The first permanent settlements were being built. Stonehenge wouldn't be constructed for another 5,000 years. The pyramids of Egypt were still 8,000 years in the future. Writing hadn't been invented. Metalworking hadn't been invented. The wheel hadn't been invented. If you had started traveling at the speed of light from one end of the Orion Arm 10,000 years ago, at the very dawn of human civilization, you would just now be arriving at the other end. That's how long the Orion Arm is. It spans the entire history of civilization, and then some, measured in light travel time. And remember, nothing can actually travel at the speed of light. Real spacecraft travel far slower. At the speed of the Parker Solar Probe, crossing the length of the Orion Arm would take approximately 16 million years. That's not a number that connects to anything in human experience. 16 million years ago, great apes were just beginning to diverge from other primate lineages. The ancestors of modern humans were still millions of years away from existing. The entire evolutionary journey from early apes to modern Homo sapiens took less time than it would take our fastest spacecraft to cross the Orion Arm. The width is equally staggering. At 3,500 light years across, Even traversing the Orion Arm from one side to the other, the short way, would take 3,500 years at light speed. That's roughly the span from the height of ancient Egypt's New Kingdom to the present day. From the time of Ramesses the Great to right now, this very moment, that's approximately how long light takes to cross the width of the structure we live in. And this is a feature that textbooks call minor. This is the structure that diagrams show as a thin little bridge, barely worth mentioning. Now here's where those diagrams really deceive us. When you look at a typical illustration of the Milky Way from above, the kind you see in science textbooks, documentaries, or websites, the entire galaxy is usually drawn on an image that might be 30 centimeters across on your screen or on a printed page. The Milky Way is roughly 100,000 light years in diameter. So on a 30 centimeter diagram, each centimeter represents about 3,300 light years. The Orion Arm, at 10,000 light years long, occupies about 3 centimeters on that diagram. 3 centimeters. About the width of a large coin. And its width of 3,500 light years corresponds to roughly 1 centimeter. 1 centimeter. That's the width of your little finger. When you look at those diagrams and see the Orion Arm as a tiny feature, your brain is processing 3 centimeters of ink on a page, but those 3 centimeters represent 10,000 light years of real physical space. That 1 centimeter of width represents 3,500 light years. Every millimeter on that diagram corresponds to hundreds of light years. Every fraction of a millimeter contains distances that humanity could never cross. The diagram has taken something incomprehensibly vast and compressed it into something your eye processes as small. And because your brain is evolved to judge size based on visual proportions, it looks at the Orion Arm on the diagram, compares it to the sweeping major arms that span 20 or 30 centimeters, and concludes that the Orion Arm is insignificant. But the Orion Arm isn't insignificant. The diagram is just lying to you, not intentionally. There's no way to draw a galaxy to true scale on a piece of paper and still have it be useful. The problem is inherent to the act of representation. You cannot put 100,000 light years on a page and expect a human brain to correctly interpret the scale of each feature. The compression is too extreme. The information loss is too great. Your visual system treats the diagram as if it were a photograph of something you could hold in your hands, and it judges sizes accordingly. But this is not a photograph. It's a compression of distances so extreme that the smallest visible feature on the diagram still represents thousands of light years of actual space. Think about it this way. Imagine you drew a map of the United States on a standard piece of paper. The distance from New York to Los Angeles is about 4,500 kilometers. On a typical printed map, that distance might span about 25 centimeters. Now, imagine that somewhere on that map, there's a feature label that's about half a centimeter wide. Your brain would register that feature as small. A tiny thing. Barely noticeable on the map. But half a centimeter on that map represents roughly 90 kilometers. 90 kilometers is a huge distance on the ground. It's the distance from one major city to another. You couldn't walk it in a day. You couldn't see from one end to the other. It contains towns, rivers, forests, farms, thousands of buildings, tens of thousands of people. It's a vast area of land that contains enormous complexity and enormous distance. But on the map, it's half a centimeter. And your brain says small. That's what's happening with the Orion Arm on galaxy diagrams. Except the compression is millions of times more extreme. The Orion Arm isn't 90 kilometers, it's 10,000 light years, and it's been squeezed down to a few centimeters on a page that you glance at for a few seconds, before moving on, never realizing that those few centimeters contain more space than human beings could explore in millions of lifetimes. Let me make this even more concrete by talking about what's actually inside the Orion Arm. Because it's not empty space. It's not a sparse scattering of a few nearby stars. The Orion Arm is packed with stellar activity, with famous astronomical objects, with star-forming regions, with nebulae, with clusters, with worlds. Some of the most iconic objects in the entire night sky are inside the Orion Arm with us, the Orion Nebula. If you've ever seen a photograph of a glowing cloud of gas with young stars burning inside it, there's a good chance it was the Orion Nebula. It's one of the most photographed objects in astronomy. It sits about 1,340 light-years from Earth, well within the Orion Arm. The nebula itself is about 24 light-years across, a vast stellar nursery where new stars are actively being born. Inside the Orion Nebula, clouds of hydrogen gas are collapsing under their own gravity, heating up and igniting nuclear fusion. Hundreds of young stars have already formed there, and more are forming right now. Some of them are surrounded by protoplanetary disks, swirling rings of dust and gas that will eventually coalesce into planets. Future solar systems are being built inside the Orion Nebula at this very moment, and the Orion Nebula is just one star-forming region among many within our arm of the galaxy. The Cygnus star-forming complex is another enormous region of stellar birth within the Orion Arm. Located roughly 4,000 to 5,000 light-years from Earth, toward the constellation Cygnus, this complex contains multiple giant molecular clouds, stellar nurseries, and some of the most massive and luminous stars known in our region of the galaxy. The Cygnus complex includes objects like the Cygnus OB2 association, one of the most massive star-forming regions in the entire Milky Way, containing thousands of young stars, some of them dozens of times more massive than the Sun. These massive stars burn through their fuel at a furious rate, shining millions of times brighter than the Sun, but living for only a few million years before dying in spectacular supernova explosions. The Cygnus region is a powerhouse of stellar activity, and it's inside the Orion Arm. Betelgeuse, one of the most famous stars in the sky, is inside the Orion Arm. It sits about roughly 550 to 700 light-years from Earth, depending on which measurement you use, because pinning down the distance to a star that's actively pulsating and changing size is genuinely difficult. Betelgeuse is a red supergiant, a massive star nearing the end of its life. It's so enormous that if you placed it where the Sun is, its outer atmosphere would extend past the orbit of Mars and likely reach or even exceed the orbit of Jupiter. Betelgeuse will eventually explode as a supernova, and when it does, it will briefly shine as bright as the full moon in Earth's sky, visible even during the daytime. That explosion could happen tomorrow, or it could happen 100,000 years from now. We don't know. But whenever it happens, it will be an event within the Orion Arm. One of our neighbors going out in a blaze of glory. The Crab Nebula is inside the Orion Arm. This is the remnant of a supernova that exploded in the year 1054. Chinese astronomers recorded seeing a new star appear in the sky, bright enough to be visible during the day for 23 days. What they were seeing was a massive star about 6,500 light-years away, detonating at the end of its life. Today, the remnant of that explosion is a rapidly expanding cloud of gas and debris, about 11 light-years across, with a pulsar at its center, a rapidly spinning neutron star that emits beams of radiation like a cosmic lighthouse. The Crab Nebula is one of the most studied objects in astronomy, and it's inside our arm. The Vela supernova remnant is within the Orion Arm. This is the remains of a star that exploded roughly 11,000 years ago, about 800 light-years from Earth. When it exploded, it would have been extraordinarily bright in the sky, easily visible to the humans living at that time, though no written record exists, because writing hadn't been invented yet. The Vela remnant is now a vast expanding shell of hot gas, about 100 light-years across. The Gum Nebula, one of the largest emission nebulae in the sky, is within the Orion Arm. It spans roughly 36 degrees of the sky as seen from Earth, which is enormous. For reference, the full moon covers about half a degree. The Gum Nebula covers an area of sky roughly 70 times the diameter of the full moon. It's located about 1,500 light-years from Earth and spans roughly 1,000 light-years across. This is a single object within the Orion Arm that is itself 1,000 light-years in extent. And these are just the famous objects, the ones that have names, the ones that show up in textbooks and on astronomy websites. The Orion Arm contains vastly more than these celebrated landmarks. It contains millions of ordinary stars, red dwarfs, yellow dwarfs like our Sun, orange dwarfs, white dwarfs, brown dwarfs. It contains binary systems and triple systems and quadruple systems. It contains planetary nebulae, the glowing shells of gas puffed off by dying sun-like stars. It contains open clusters, groups of young stars born together from the same molecular cloud. The Pleiades, that beautiful cluster of hot blue stars about 440 light-years away, is inside the Orion Arm. The Hyades cluster, about 150 light-years away, is inside the Orion Arm. Virtually everything you can see in the night sky with your naked eye is inside the Orion Arm, because the Orion Arm is our home, and the stars visible to the naked eye are all relatively nearby on galactic scales. Here's something that helps make the scale tangible. Within roughly 400 light-years of the Sun, a tiny fraction of the Orion Arm, astronomers have catalogued tens of thousands of individual star systems. The European Space Agency's Gaia spacecraft, which has been mapping the positions and motions of stars with extraordinary precision, has measured over 1 billion stars in the Milky Way. A substantial fraction of those billion measured stars are within the Orion Arm. The Arm isn't sparse, it's rich with stellar populations, it's dense with activity, it contains everything from calm, stable star systems like ours, to violent, chaotic regions where massive stars are being born and dying in rapid succession. Consider that our immediate stellar neighborhood, the region within about 50 light-years of the Sun, contains roughly 2,000 known stars. That's just 50 light-years. The Orion Arm is 10,000 light-years long and 3,500 light-years wide. The volume of the Orion Arm is incomparably larger than that tiny 50 light-year bubble. Estimates vary, but the Orion Arm is thought to contain somewhere in the range of several billion stars. Billions, not millions, billions. Each one a sun, many of them with their own planets. Some of those planets are rocky worlds orbiting in their star's habitable zone, where liquid water could exist on the surface. Every single one of those stars exists within this feature that diagrams draw as a thin little bridge between two larger arms. And those billions of stars almost certainly have planets. This isn't speculation, it's based on hard data. NASA's Kepler Space Telescope, which operated from 2009 to 2018, spent years staring at a single patch of sky, monitoring over 150,000 stars for the tiny dips in brightness that occur when a planet passes in front of its host star. What Kepler found transformed our understanding of how common planets are. Before Kepler, we didn't know whether planets were rare or abundant. After Kepler, the answer was clear. Planets are everywhere. The data showed that on average, every star in the Milky Way has at least one planet. Many stars have multiple planets. Some have entire systems with 5, 6, 7 or more worlds orbiting them. Rocky planets, roughly the size of Earth, turned out to be particularly common, far more common than anyone had predicted before the mission. Kepler's successor, the TESS mission launched in 2018, has continued finding planets around nearby stars, confirming and extending Kepler's results. When you apply these occurrence rates to the Orion Arm, the numbers become staggering. If the Orion Arm contains several billion stars, and the average star has at least one planet, then the Orion Arm contains at least several billion planets. But many stars have multiple planets, and the average based on Kepler data is closer to 1.5 to 2 planets per star. That pushes the number of worlds in the Orion Arm toward 10 billion or more. 10 billion planets. Some are gas giants like Jupiter, massive spheres of hydrogen and helium swirling with storms larger than Earth. Some are ice giants like Neptune, cold and distant from their stars. Some are rocky worlds like Earth or Mars, with solid surfaces and potentially complex geology. And some fraction of those rocky worlds orbit in their star's habitable zone. the region where temperatures could allow liquid water to exist on the surface. Estimates vary, but roughly 1 in 5 Sun-like stars may have a rocky planet in its habitable zone. For red dwarfs, which are the most common type of star, the fraction may be even higher. This means the Orion Arm likely contains hundreds of millions of rocky planets in habitable zones, hundreds of millions of worlds where, at least in principle, conditions might be right for liquid water and potentially for life. All of them inside this one structure. All of them inside those 3 centimeters on a textbook diagram. Every single one of them unknown to us, unexplored, unnamed, waiting in the darkness between the stars. Let me try one more way to make you feel this. Imagine you could magically freeze time and teleport yourself to a random location inside the Orion Arm, somewhere far from the sun, perhaps 3,000 light years away in a region you've never observed directly. What would you find? You'd find stars. Stars in every direction. You'd find gas clouds and dust lanes. You might find yourself near a star-forming nebula, watching raw matter condense into new suns. You might find yourself in a quiet region between molecular clouds, surrounded by scattered older stars going about their ancient orbits. You'd find planetary systems. Many of the stars you'd see would have planets. Some would have gas giants, some would have rocky worlds, some would have ice worlds. You'd find a region of space as rich and complex as the region around the sun, filled with its own astronomy, its own neighborhoods, its own stellar dynamics. And you could explore that region for 1 million years, and never run out of new things to find. Then, you could teleport to another random location in the Orion Arm, and find an equally complex, equally rich environment. You could do this 1,000 times, 1 million times, and each location would be different. Each would have its own character, its own stellar populations, its own clouds and clusters and worlds. That's what's inside those 3 centimeters on a textbook diagram. This is why understanding the Orion Arm matters. Not because it's the biggest feature in the galaxy. It's not. The major arms are bigger. The galaxy as a whole is far bigger. But the Orion Arm demonstrates something crucial about how badly our intuition fails at galactic scales. When you see a galaxy diagram and your brain registers the Orion Arm as small, something has gone terribly wrong in the translation from reality to perception. The Orion Arm isn't small by any meaningful standard. It's only small relative to the galaxy's major spiral arms. And those major arms are so absurdly, incomprehensibly large that being smaller than them doesn't make you small. It just makes you less incomprehensibly large. The problem is that we don't have a word for that. We don't have a language that easily distinguishes between actually small and merely smaller than something that defies comprehension. So our brains default to the visual shortcut. It looks smaller on the diagram, therefore it must be small. But it's not. It's enormous. It contains billions of stars, thousands of light years of distance, some of the most spectacular objects in the night sky, and more worlds than we could ever count. The Orion Arm is a colossal structure. We just happen to live inside it, which means we can't step back and see it properly. And every diagram that tries to show it to us ends up accidentally convincing us it's insignificant. The measurements keep improving. Every year, new data refines our picture of the Orion Arm. The Gaia spacecraft, launched in 2013 by the European Space Agency, has been revolutionizing our understanding of the Milky Way's structure by measuring the positions, distances, and motions of billions of stars with unprecedented accuracy. Before Gaia, much of what we knew about spiral arm structure came from radio observations of hydrogen gas and the positions of particularly bright young stars and HII regions, ionized hydrogen clouds that glow brightly near hot stars. These methods gave us a rough picture but left enormous uncertainties. Gaia changed everything by providing precise distances to individual stars across huge swaths of the galaxy. With Gaia data, astronomers have been able to trace the spiral structure in far more detail. And one of the findings that emerged from this data is that the Orion Arm may be more significant than we previously thought. Rather than a short, stubby spur connecting two larger arms, the Orion Arm may extend farther than traditional maps showed. Some analyses suggest it could be longer, possibly reaching 20,000 light-years or more, which would make it comparable to some definitions of a full spiral arm rather than just a minor spur. The pitch angle of the Orion Arm, the angle at which it inclines relative to the galaxy's circular structure, has also been measured more precisely. This pitch angle is consistent with it being a genuine arm segment, rather than a random interarm feature. The question of whether the Orion Arm is a spur, a branch, or a full arm remains an active area of research. But what's clear from the data is that it's a more substantial structure than older maps implied. We may need to update our mental picture of the Milky Way to give the Orion Arm more prominence. Not because it rivals the Perseus or Scutum Centaurus arms, but because it's a bigger deal than the traditional little spur interpretation suggested. None of this changes the fundamental point though. Whether the Orion Arm is 10,000 light-years long or 20,000 light-years long, whether it's a spur or a branch or a full arm, it remains a structure of staggering scale. A structure that contains our entire existence. Every human being who has ever lived, every star we've ever seen, every planet we've ever studied, all of it is inside this one feature of the Milky Way. And that feature, regardless of its exact classification, is so vast that light itself needs thousands of years to cross it. That is the true scale of the Orion Arm, not what it looks like on a diagram, not how it compares visually to the Perseus Arm, but what it actually is in physical terms. A region of space so large that it dwarfs everything in human experience, everything in human history, and everything humanity has ever accomplished in the realm of space exploration. We have traveled to the moon, 384,000 kilometers away. We have sent probes to the outer solar system, billions of kilometers from Earth. Voyager 1, our most distant spacecraft, is about 24 light hours from the Sun, and the Orion Arm, this minor spur, this afterthought on a galaxy map, is 10,000 light-years long. The difference between what we've explored and what the Orion Arm contains is a difference so vast that it makes all of human space exploration look like a single footstep in a journey that would take millions of lifetimes to complete. That is what flat diagrams hide from you. That is what those clean, simple, color-coded images of the Milky Way fail to communicate. The Orion Arm isn't a footnote. It's a universe unto itself, hiding in plain sight on every galaxy map ever drawn, compressed into a sliver that your eye skips over on its way to the more impressive-looking features. But those few centimeters on the page contain everything we have ever known. Now that you understand the true dimensions of the Orion Arm, let's put it next to the galaxy's major features. Because the Orion Arm doesn't exist in isolation. It sits between two of the Milky Way's great spiral arms. And understanding those arms, understanding how they compare to the Orion Arm in size, in mass, and in activity, is what truly reveals the paradox of scale we're dealing with tonight. The Orion Arm is enormous, we've established that. But when you place it next to the structures that flank it, you start to understand why diagrams make it look so small. Not because it is small, but because the major arms of the Milky Way operate on a scale that makes even an enormous structure look modest. Let's start with the Perseus Arm, the major spiral arm that lies outward from us, farther from the galactic center. The Perseus Arm is one of the two primary arms of the Milky Way in most structural models. It stretches for roughly 30,000 to 40,000 light-years along its length, curving in a grand spiral around a significant portion of the galaxy. Some estimates put it even longer, depending on where you define its beginning and end, because spiral arms don't have clean edges. They fade gradually into the interarm regions, with star density declining slowly rather than dropping off sharply. The Perseus Arm is not just long, it's also wide and massive. It contains some of the most active star-forming regions in the entire galaxy. Giant molecular clouds within the Perseus Arm are churning out new stars at prodigious rates. The arm is rich in young, hot blue stars, the kind that burn bright and die fast, and it's lined with enormous HEI regions, vast clouds of ionized hydrogen that glow pink and red around clusters of massive young stars. The Perseus Arm is a dominant feature of the galaxy. If you could see the Milky Way from outside, from a distance of millions of light years, the Perseus Arm would be one of the first things you'd notice. A bright, sweeping curve of blue and white light, tracing a spiral path through the galaxy's disk. Now, compare. The Perseus Arm is roughly 30,000 to 40,000 light years long. The Orion Arm is roughly 10,000. The Perseus Arm is 3 to 4 times longer. That's a significant difference. On a galaxy diagram, the Perseus Arm looks appropriately grand, sweeping in a long curve, while the Orion Arm looks like a short connector between larger features. And that visual comparison is roughly correct in terms of proportions. The Perseus Arm really is several times longer. But here's what the visual comparison doesn't tell you. Even though the Orion Arm is shorter, it's still 10,000 light years long. 3 times shorter than the Perseus Arm doesn't mean small. It means shorter than something that's staggeringly long. If I told you one mountain is 30,000 feet tall and another is 10,000 feet tall, the second mountain is shorter, sure, but it's still 10,000 feet tall. That's still a mountain. Nobody would look at a 10,000 foot peak and call it insignificant just because a taller mountain exists somewhere else. But that's exactly what we do with the Orion Arm when we compare it to the Perseus Arm on a diagram. We see the size difference and our brains conclude that the smaller one must be small. It's not. It's just smaller. Inward from our position, closer to the galactic center, lies the Sagittarius Carina Arm. This is the other major arm in our region of the galaxy. The Sagittarius Arm sweeps past us on the inner side, between us and the galactic center, curving around the galaxy in a spiral that mirrors the Perseus Arm on the other side. The Sagittarius Carina Arm is estimated to stretch for at least 30,000 light years, possibly longer. Like the Perseus Arm, it's rich with star formation. When you look toward the constellation Sagittarius in the summer sky, you're looking through the Sagittarius Arm toward the galactic center. The dense star fields you see in that direction, the milky glow that gives our galaxy its name, much of that light comes from stars in the Sagittarius Arm and the denser regions beyond it. The Sagittarius Arm contains some spectacular objects. The Eagle Nebula, famous for the Hubble Space Telescope's iconic Pillars of Creation photograph, is in the Sagittarius Arm, roughly 7,000 light years from Earth. Those pillars are columns of gas and dust, light years tall, sculpted by the radiation from nearby hot young stars, and inside them, new stars are being born. The Omega Nebula, also called the Swan Nebula, is another massive star-forming region in the Sagittarius Arm, about 5,000 to 6,000 light years away. These objects are part of the Arm's intense stellar production. So now we have the picture. The Orion Arm is flanked on both sides by spiral arms that are 3 to 4 times its length. Arms that contain enormous star-forming complexes and billions of stars spread across tens of thousands of light years. The Orion Arm sits between them like a bridge, shorter in extent, less prominent in galactic structure, but still containing billions of stars and thousands of light years of distance within its own boundaries. But these aren't even the biggest features. The Scutum Centaurus Arm is often considered the most massive and prominent arm in the entire Milky Way. It originates from one end of the galaxy's central bar and sweeps outward in an enormous spiral that wraps around a huge fraction of the galaxy. Depending on how you trace it, the Scutum Centaurus Arm may extend for 60,000 light years or more. Some models suggest it's the single most substantial arm in the galaxy, containing the highest density of stars and gas of any spiral feature. The Scutum Centaurus Arm passes through some of the richest star-forming regions in the Milky Way, including areas near the galactic bar where gas is funneled inward and compressed. triggering intense bursts of stellar birth. The arm is home to some of the most luminous star clusters in the galaxy, collections of thousands of massive hot stars that outshine anything in our local stellar neighborhood. Then there's the Norma Arm, located even closer to the galactic center. The Norma Arm isn't as long as the Scutum Centaurus or Perseus arms, but it's positioned in a region of the galaxy where stellar density is much higher. Near the galactic center, everything is compressed. Stars are packed more tightly, gas clouds are denser, and the gravitational environment is more extreme. The Norma Arm exists in this denser environment, and it's associated with some of the most luminous HII regions in the galaxy. And beyond the Perseus Arm, in the outer reaches of the galaxy, lies the Outer Arm. This feature extends into the galaxy's sparse outskirts, where star density drops off and the disk of the galaxy begins to thin out. The Outer Arm is less well studied because it's far away and partially obscured, but it adds another layer to the galaxy's spiral structure. When you look at all these arms together, the full spiral structure of the Milky Way, the Orion Arm's relative position becomes clear. It is genuinely a smaller feature sitting between much larger features. The major arms wrap around the galaxy for tens of thousands of light years. Some of them may extend for more than half the galaxy's circumference. The Orion Arm, at roughly 10,000 light years, spans only a fraction of what the major arms cover. In terms of star formation activity, the major arms outpace the Orion Arm significantly. The density waves in the major arms compress gas more intensely, triggering more prolific star birth. The Orion Arm has star-forming regions, certainly. The Orion Nebula, the Cygnus Complex, these are real and active stellar nurseries. But they're modest compared to the enormous star-forming factories in the Scutum Centaurus or Perseus arms. In terms of sheer mass, the major arms contain far more gas, dust, and stars than the Orion Arm. If you weighed the Orion Arm against the Perseus Arm would come out substantially heavier. More material, more stars, more everything. The Orion Arm is a lighter structure, less dense, less active, less massive. But here's the thing that needs to be said clearly and emphatically. None of that makes the Orion Arm small. Less massive than the Perseus Arm is not the same as small. Less active in star formation than the Scutum Centaurus Arm is not the same as insignificant. The Orion Arm is shorter, lighter, and quieter than the major arms, but it's still a structure containing billions of stars spread across thousands of light years. It's like comparing a river to an ocean. The river is smaller, obviously, but nobody calls a river insignificant. Nobody looks at the Amazon River and says it's tiny because the Pacific Ocean exists. The river is a massive feature in its own right, even if there are larger bodies of water elsewhere. Let's also talk about the galactic center, because that's another structure that puts the Orion Arm in perspective while simultaneously showing how everything at galactic scale defies normal comprehension. The galactic center is roughly 26,000 light years from us. At the very heart of the Milky Way sits Sagittarius A star, the supermassive black hole with a mass of about 4 million times the mass of the Sun. The region around Sagittarius A star is extraordinarily dense. Stars are packed far more tightly than in our neighborhood. Some stars orbit the black hole at enormous velocities. One star, called S2, completes an orbit around Sagittarius A star every 16 years, reaching speeds of about 3% of the speed of light at its closest approach. That's roughly 9,000 kilometers per second. For comparison, our Sun plods along at 230 kilometers per second in its orbit, around the galactic center. S2 is moving almost 40 times faster. The central bar of the galaxy, that beam-like structure of old stars that runs through the heart of the Milky Way, spans roughly 27,000 light years. The bar alone is nearly 3 times the length of the Orion Arm. If you place the Orion Arm alongside the galactic bar for comparison, the Orion Arm would look like a small extension off to one side. And the bar isn't even the most dramatic feature of the galactic center. the galactic bulge, the dense spheroidal concentration of stars surrounding the bar, is roughly 10,000 light years across. That's comparable to the length of the entire Orion Arm. The bulge alone, which is just one component of the galactic center, contains a volume of space roughly equivalent in extent to our entire arm. And within that volume, the density of stars is vastly higher. The galactic bulge is packed with old red and orange stars, billions of them concentrated into a relatively compact region. The night sky as seen from inside the bulge would be spectacular, ablaze with countless stars far brighter and more numerous than anything visible from our quiet position in the Orion Arm. This comparison is striking. The length of the galactic bar is roughly 27,000 light years. The diameter of the galactic bulge is roughly 10,000 light years. The length of the Orion Arm is roughly 10,000 light years. The Orion Arm, which holds everything we've ever known, is comparable in extent to the galactic bulge alone. And the bulge is just the central condensation of the galaxy, a dense knot at the heart of a structure that extends 100,000 light years across. The Orion Arm is a feature whose dimensions match those of the galactic core region, and yet the core is just one small part of the whole. This tells you something about the galaxy's scale. When even the comparison points are themselves enormous, the thing you're trying to measure begins to lose all connection to anything in human experience. Now, I mentioned earlier that our understanding of the Orion Arm has been changing, and this deserves more attention. Because the story of how we map the Orion Arm is itself a story about how difficult it is to understand the structure of something you're inside of, and how our picture keeps getting revised as our tools improve. For most of the 20th century, our knowledge of the Milky Way's spiral structure came primarily from radio astronomy. Hydrogen gas, which is abundant throughout the galaxy, emits radio waves at a very specific wavelength, about 21 centimeters. By observing this 21 centimeter emission and measuring the Doppler shift of the radio waves, astronomers could figure out how fast the hydrogen gas was moving relative to us. Since the gas orbits the galactic center at speeds that depend on its distance from the center, the Doppler shift could be used to estimate how far away each cloud of gas was. This technique, called the kinematic distance method, allowed astronomers to map the distribution of hydrogen gas throughout the galaxy and trace the spiral arms. It was a powerful tool, but it had significant limitations. The kinematic distance method relies on assumptions about how the galaxy rotates. If the rotation isn't perfectly smooth, if there are local motions or disturbances, the distance estimates can be way off. Near the galactic center and near the sun's own orbital distance, the method breaks down almost completely because the Doppler shifts become ambiguous. This is particularly problematic for mapping the Orion Arm, because the Orion Arm is right where we are. The method works best for distant features and worst for nearby ones. It's an ironic situation. The hardest part of the galaxy to map is the part we live in. Another traditional method used the positions of bright young stars and HOI regions as tracers of spiral structure. Hot, massive, blue stars, and the glowing nebulae they illuminate tend to be concentrated in spiral arms because that's where star formation happens. By plotting the positions of these objects, astronomers could trace out the arms. But again, distance measurements were often uncertain, especially before Gaia. Many distances were estimated using indirect methods like spectroscopic parallax, where you estimate a star's distance by comparing its apparent brightness to its expected brightness based on its spectral type. These estimates had large error bars, sometimes 30% or more. When you're trying to map a structure that's thousands of light years across, a 30% error on distance measurements means your map is blurry. Features might appear to be in the wrong place. Connections between structures might be real or might be artifacts of measurement error. This is why the classification of the Orion Arm kept shifting. Early maps based on radio observations suggested it was a short, minor spur connecting the Sagittarius and Perseus arms. Other studies suggested it might be longer. Some suggested it was an independent arm segment rather than a true spur. The data simply weren't precise enough to settle the question definitively. Then, Gaia arrived. The European Space Agency launched the Gaia spacecraft in 2013 with a mission to create the most precise three-dimensional map of the Milky Way ever made. Gaia measures the positions, debris, distances, and motions of stars using a technique called astrometric parallax. As the spacecraft orbits the Sun, it measures how stars appear to shift against the background due to Earth's motion, the same parallax method that has been used for centuries, but executed with space-based precision that ground-based telescopes cannot match. Gaia has now measured parallaxes for nearly 2 billion stars, providing accurate distances to stars thousands of light years away. This is a game changer for mapping galactic structure. Instead of relying on indirect distance methods with large uncertainties, astronomers can now use direct geometric distances for millions of stars. They can trace the three-dimensional positions of young stars, star-forming regions, and stellar clusters across huge volumes of the galaxy. The results have been revelatory. Studies using Gaia data have found that the Orion Arm appears to be more substantial than older maps indicated. Several research teams have traced the arm using young stellar populations, open clusters, and classical Cepheid variable stars, which are excellent distance markers because their pulsation periods are directly related to their intrinsic luminosities. These studies suggest the Orion Arm may extend significantly farther than the traditional 10,000 light-year estimate. Some analyses trace it out to 15,000 or even 20,000 light-years, which would make it comparable in length to some definitions of a major arm. The pitch angle of the Orion Arm has been measured at roughly 10 to 12 degrees, which is broadly consistent with the pitch angles of the galaxy's major arms. A spur or minor feature might be expected to have a different pitch angle from the major arms, but the Orion Arm's pitch angle fits right into the range of the larger structures. This suggests it may be more structurally similar to a major arm than the traditional spur classification implies. Parallax measurements of masers have provided another line of evidence. Masers are natural sources of microwave radiation found in star-forming regions. They act like cosmic lighthouses, emitting intense, narrowly focused radio waves. Because they're associated with star formation, they tend to be located in spiral arms. Using very long baseline interferometry, a technique that combines data from radio telescopes spread across continents or even across the globe, astronomers have measured extremely precise distances and motions for masses in various parts of the Milky Way, including the Orion Arm. These massive measurements have helped confirm that the Orion Arm is a coherent, elongated structure with real physical extent, not just a random clumping of stars between two larger arms. The masers trace a clear spiral feature that aligns with the arm's expected position and orientation. So the emerging picture from modern data is this. The Orion Arm is more substantial than we thought. It may be longer, more coherent, and more structurally significant than the traditional short spur interpretation. Some astronomers now prefer to call it the local arm rather than the Orion spur, reflecting its upgraded status. Others maintain that it's still a secondary feature, smaller than the Perseus or Scutum Centaurus arms, even if it's bigger than we previously realized. The debate is ongoing, and it may take more data to resolve it fully. But regardless of where the classification lands, the key point remains the same. Whether the Orion Arm is a spur, a branch, or a minor arm, it is a structure of immense scale. If new data shows it's 20,000 light-years long instead of 10,000, that makes it twice as large as we thought, which only strengthens the argument that diagrams have been drastically understating its significance. And if it turns out to be a genuine arm rather than a spur, that reshapes our understanding of the Milky Way's structure itself, suggesting that the galaxy may have more complexity and more intermediate scale features than simple 2-arm or 4-arm models predict. What hasn't changed is our position within it. The Sun still sits roughly in the inner edge of the Orion Arm, about 26,000 light-years from the galactic center. We're still between the Sagittarius and Perseus arms. We're still in a relatively quiet part of the galaxy, away from the most intense star-forming regions, sheltered from the worst of the supernova activity that rages in the major arms. Our location hasn't moved. What's changed is our understanding of the feature we live in. It's bigger and more important than we realized, and that, in a way, is reassuring. We're not in the most insignificant scrap of the galaxy. We're in a substantial structure, a real arm or arm-like feature, one that spans thousands upon thousands of light years and contains billions of stars and all the raw material needed for star and planet formation to continue for billions of years into the future. Let me bring in one more comparison to help crystallize how the Orion Arm relates to the wider galaxy. The Milky Way is about 100,000 light years in diameter. If you draw a line straight through the center of the galaxy from one edge of the disk to the other, that line is 100,000 light years long. The Orion Arm at 10,000 light years is about 10% of that diameter. That might sound like a reasonable fraction, but remember, the galaxy isn't one-dimensional. It's a disk. The area of the galactic disk is far greater than a simple diameter measurement suggests. And the spiral arms don't just span the diameter, they wrap around the galaxy, covering much more distance than a straight line across. The Perseus arm, for instance, curves around a significant portion of the galaxy's circumference. The galaxy's circumference at the sun's distance from the center, using a simplified circular approximation, is roughly 160,000 light years. The Perseus arm might extend across a quarter or more of that circumference, meaning it covers 40,000 light years or more of the galaxy's perimeter. The Orion Arm, at 10,000 light years, covers roughly 6% of that circumference. That gives you a sense of how the Orion Arm relates to the galaxy as a whole. It's a real feature, covering a meaningful fraction of our ring of the galaxy, but it's a modest fraction compared to the sweeping arcs of the major arms. And yet, 6% of the Milky Way's circumference at our orbital distance is still 10,000 light years. 6% sounds small. It sounds like a trivial fraction. But when 6% of something equals 10,000 light years, the absolute scale is still breathtaking. This is the trap that percentages and fractions set for our intuition. When someone tells you the Orion Arm is a small fraction of the galaxy, your brain hears small and files it away as unimportant. But a small fraction of something that is 100,000 light years across is still enormous by any standard that makes sense in human terms. 1% of the galaxy's diameter is 1,000 light years. 1/10 of 1% is 100 light years. Even the tiniest fractions of the Milky Way correspond to distances that are utterly beyond human capability to traverse. The galaxy is so large that even its small features are vast. This is the central lesson of comparing the Orion Arm to the major arms and the wider galactic structure. The comparison shows that the Orion Arm is a secondary feature. It's shorter than the major arms, less massive, less active in star formation, smaller in every measurable dimension. That's a fact. But the comparison also reveals something deeper. It reveals that the scale of the galaxy is so extreme that even secondary features, even minor spurs, even the smallest identifiable structures in the spiral pattern are still mind-bogglingly large. The Orion Arm is to the Milky Way what a hill might be to a mountain range. It's smaller than the peaks surrounding it, but it's still a feature that rises thousands of feet above the plane, containing rivers and forests and ecosystems of its own. It's only small in relative terms. In absolute terms, it's anything but. The galaxy has a way of humbling everything within it. The Sun, which is a star so massive it contains 99.86% of all the mass in the solar system, is just one ordinary star among hundreds of billions. The solar system, which extends for billions of kilometers in every direction from the Sun, occupies an infinitesimal fraction of the Orion Arm's volume. The Orion Arm, which contains billions of stars and stretches for thousands of light years, is just one feature among several in the Milky Way's spiral structure. And the Milky Way itself is just one galaxy among trillions in the observable universe. Each level of the hierarchy dwarfs the one below it so completely that the smaller level becomes invisible. You can't see the solar system from outside the Milky Way. You can't distinguish the Orion Arm from a photograph of the whole galaxy taken from millions of light years away. Everything gets swallowed by the next level of scale. But that doesn't mean the smaller levels don't matter. The solar system matters because it contains Earth. The Orion Arm matters because it contains the solar system and billions of other star systems, many of which might harbor their own worlds, their own chemistries, maybe their own forms of life. The Milky Way matters because it contains the Orion Arm and every other arm, bar, bulge, and halo component that makes up our galactic home. Scale isn't the same as significance. The Orion Arm is a secondary feature of the Milky Way, but it's the secondary feature we live in. It's where every human who has ever existed has spent their entire life. It's where every star visible to the naked eye resides. It's the structure within which our entire civilization has unfolded. From the first stone tools to the space telescopes orbiting Earth right now. Its relative smallness on a galactic map doesn't diminish what it contains. And what it contains is everything we know, everything we've explored, and everything we are. That is not small. That can never be small. It's only drawn that way because the galaxy refuses to fit on a page without compressing everything inside it down to nothing. So now you understand the structure. You understand what the Orion Arm is, where it sits in the galaxy, how large it is in absolute terms, and how it compares to the major spiral arms that flank it. But there's one more layer to this story, and it might be the most important one. Because everything we've talked about so far has been zooming out. We've been pulling back, comparing the Orion Arm to bigger and bigger things, watching it shrink in relative terms even as its absolute size remained staggering. Now, I want to do the opposite. I want to zoom in. I want to look at just our local region of the Orion Arm, the small patch of this structure that surrounds the Sun, and show you that even this tiny corner of a minor galactic feature is so vast that it breaks every intuition you have about distance, time, and exploration. Let's start close, really close. The Sun's immediate neighborhood. Within about 15 light years of the Sun, there are roughly 50 known star systems. That's a sphere 30 light years across, centered on us, containing about 50 stars or star systems. Some of them single stars, some binaries, a few triples. You might recognize some of the names. Proxima Centauri, the nearest star, at 4.24 light years. Alpha Centauri A and B, the binary pair that Proxima orbits, at about 4.37 light years. Barnard's star, about 6 light years away. Wolf 359, about 7.9 light years. Lalande 21185, about 8.3 light years. Sirius, about 8.6 light years. These are our closest stellar neighbors, the stars right next door by galactic standards. And even this tiny neighborhood, this sphere just 30 light years across, is so large that reaching any of these stars with current technology would take thousands of years. Voyager 1, our most distant spacecraft, has been traveling for nearly 50 years and has covered about 1 light day. 1 light day. The nearest star is 4.24 light years away. Voyager has covered roughly 1/1500th of the distance to the nearest star in half a century of continuous travel. At its current speed, it would need about 73,000 years to reach Proxima Centauri, if it were heading in that direction, which it's not. So even within 15 light years, within this tiny bubble that represents a vanishingly small fraction of the Orion Arm, the distances are effectively infinite for human technology. We can see these stars, we can study them with telescopes, we can measure their distances, their masses, their temperatures, their compositions, but we cannot visit them. Not with anything we can build today, not with anything we're likely to build in the near future. 15 light years is our immediate front yard, and we can't even cross it. Now expand that bubble. Within 100 light years of the Sun, there are roughly 14,000 known stars. 14,000 stars in a sphere 200 light years across. This region includes many of the brightest and most familiar stars in the night sky. Arcturus is about 37 light-years away. Vega is about 25 light-years. Capella is about 43 light-years. Pollux is about 34 light-years. Fomalhaut is about 25 light-years. These are the stars you see when you go outside on a clear night and look up. They're our neighbours. They're close. And yet 100 light-years is still only 1% of the Orion Arm's length. 1%. We've expanded our view to include 14,000 stars. Stars that span a volume of space it would take light a century to cross. And we've covered 1% of the arm we live in. 1 single percent. Expand again. Within 500 light-years, the number of stars climbs into the hundreds of thousands. The volume of space is now enormous, a sphere 1,000 light-years across, encompassing a huge variety of stellar populations. Within this volume, you'll find stars at every stage of their life cycle. Young, hot blue stars burning through their fuel at furious rates. Middle-aged yellow stars, like the Sun, steadily converting hydrogen to helium. Old red giants that have swollen to hundreds of times the Sun's diameter as they approach the end of their lives. White dwarfs. The dense remnants of stars that have already died. Binary systems locked in gravitational dances. Open clusters of young stars still loosely bound by the gravity that brought them together. Planetary nebulae, the glowing shells ejected by dying sun-like stars. Within 500 light-years, there is already more variety, more complexity, more astronomical richness than any human lifetime could catalogue. And 500 light-years is 5% of the Orion Arm's length. We've barely started. Before we keep expanding outward, let me pause at roughly this scale, because there's something remarkable about the region of space surrounding the Sun that most people have never heard of. It's called the local bubble, and it tells us something important about the Orion Arm's internal structure, about the fact that even within a single spiral arm, there are distinct environments, neighborhoods within neighborhoods, each shaped by events that happened millions of years ago. The local bubble is a cavity in the interstellar medium, the thin gas and dust that fills the space between stars. It's roughly 1,000 light-years across, though its shape is irregular, more like a lumpy potato than a perfect sphere. The walls of this cavity are denser than the interior, which is filled with extremely thin, hot gas. Inside the local bubble, the density of interstellar gas is much lower than in the surrounding regions of the Orion Arm. It's a relative void within the arm, a pocket of emptiness carved into the denser gas around it. How did it form? Supernovae. About 10 to 15 million years ago, a series of massive stars in our region of the Orion Arm reached the end of their lives and exploded. These weren't distant events. They happened close enough to our current location that their combined shock waves swept through the surrounding interstellar medium, pushing gas and dust outward in all directions, compressing it into a shell and leaving behind a hot, low-density cavity. The Sun didn't cause this. The Sun is a stable, middle-aged star that has never exploded and won't for billions of years. But the Sun happens to be inside the cavity that those ancient explosions created. We're floating in a bubble blown by dead stars. The local bubble isn't empty of stars. There are thousands of stars inside it, including the Sun and all of our nearest stellar neighbors. But the gas between those stars is thinner than in the surrounding Orion Arm material. This has real consequences. The density of interstellar gas affects how stars form, how radiation propagates, and what the space environment looks like for any planets within the bubble. Some researchers have even suggested that the local bubble's lower gas density might mean slightly less shielding from certain types of cosmic radiation, though the effects on Earth are debated and probably minor. What's truly fascinating is that the local bubble isn't unique. The Orion Arm is filled with structures like this. Bubbles blown by supernovae, cavities carved by stellar winds from massive stars, dense shells of compressed gas where the edges of neighboring bubbles meet and sometimes trigger new rounds of star formation. The interstellar medium within the Orion Arm isn't uniform. It's textured, layered, shaped by billions of years of stellar activity. Stars are born, they live, they die, and their deaths reshape the gas around them, creating the conditions for the next generation of stars. It's a cycle of creation and destruction that plays out across the entire arm, sculpting the environment on scales of hundreds or thousands of light years. Near the edge of the local bubble, in the compressed shell of gas along its boundary, astronomers have found active star-forming regions. The gas that was pushed outward by those ancient supernovae piled up along the bubble's walls became dense enough to begin collapsing under its own gravity and started forming new stars. The explosions that cleared our local region of space also seeded the conditions for new stellar birth at the bubble's edges. Death leading to creation. This is happening all around us, in every direction, at the boundaries of the local bubble. And we had no idea any of this existed until the last few decades, when precise measurements of interstellar gas and three-dimensional mapping of nearby stars revealed the bubble structure. In 2022, a study using Gaia data showed that essentially all nearby young star-forming regions sit on the surface of the local bubble, providing compelling evidence that the bubble itself triggered their formation. This is what exists within a region that covers roughly 10% of the Orion Arm's length. Not just stars and empty space, but structure. Complex, layered, dynamic structure shaped by millions of years of stellar evolution. Bubbles nested within the arm. Star-forming regions triggered by the deaths of earlier stars. Gas compressed into shells and filaments. The Orion Arm isn't a featureless expanse. It's an ecosystem, a landscape of interstellar environments, each with its own character and its own history, all contained within the boundaries of a single galactic feature. At 1,000 light years, the sphere is now 2,000 light years across and contains millions of stars. We're starting to encompass major astronomical landmarks. The Orion Nebula, that famous stellar nursery 1,340 light years away, is just at the edge of this volume. The Pleiades cluster, about 440 light years away, is well inside it. The Hyades cluster, about 150 light years away, is deep within it. At this scale, you're dealing with a region of space that has its own internal structure. Stars aren't randomly distributed. They cluster in groups and associations. Gas clouds form complex networks of filaments and sheets. Dust lanes block light in some directions and not others. It's a rich, textured, three-dimensional landscape of matter and energy. And it's still only 10% of the Orion Arm. 1/10. Now go to 5,000 light years, a sphere 10,000 light years across. We're now encompassing roughly half the Orion Arm's length. The number of stars in this volume runs into the billions. Billions of individual suns, each one a nuclear furnace converting elements into energy, many of them surrounded by their own families of planets. At this scale, we're including massive star-forming complexes like the Cygnus region, enormous stellar associations containing some of the most luminous stars in the galaxy. We're including supernova remnants from explosions that happened thousands of years ago. They're expanding shockwaves still plowing through the interstellar medium. We're including molecular clouds that haven't yet begun forming stars. Vast reservoirs of cold hydrogen gas waiting in the darkness for some gravitational perturbation to trigger their collapse. And at 10,000 light years, we finally encompass the full length of the Orion Arm in the traditional estimate. A sphere 20,000 light years across, centered on the Sun, would contain the entire arm and extend well into the neighboring Sagittarius and Perseus arms. But even just the Orion Arm itself, that 10,000 light-year stretch, contains more astronomical objects, more distance, more volume, more complexity than human civilization could explore or comprehend in any reasonable time frame. Let me try to put this in the starkest terms possible. The total volume of the Orion Arm, even using the conservative estimate of 10,000 light-years long, by 3,500 light-years wide, by roughly 1,000 light-years thick, because the galaxy's disk has a finite thickness, is approximately 35 billion cubic light years. 35 billion cubic light years. That's the volume of space contained within this one feature that diagrams draw as a thin sliver. Now, consider that our entire sphere of explored space, the region we've actually sent spacecraft through, extends about 1 light day from the Sun. 1 light day. The volume of that explored sphere is about 0.00000000002 cubic light years. I'll spare you the exact math, but the ratio between the volume of space humanity has explored and the volume of the Orion Arm is so extreme that the number has more than 30 zeros after the decimal point before you get to a meaningful digit. We have explored an incomprehensibly small fraction of the Orion Arm. Not a small fraction. Not a tiny fraction. A fraction so small that the human mind cannot meaningfully distinguish it from zero. Think about what that means. Everything humanity has ever done in space, every mission, every spacecraft, every orbit, every lunar landing, every Mars rover, every Voyager probe sailing through the outer solar system, all of it combined has explored a region of space that rounds to zero when compared to the Orion Arm. We haven't scratched the surface. We haven't even begun to scratch the surface. We've taken one tentative step into a room so large that the step is invisible. And this is the structure that textbooks call minor. There's another way to feel this scale. The speed of light is the absolute maximum speed in the universe. Nothing can travel faster. Light covers 300,000 kilometers every single second. It is stupendously fast by any human measure, and yet light itself, the fastest thing that exists, needs 10,000 years to cross the Orion Arm. Imagine sending a message from one end of the Orion Arm to the other. Not traveling there, just sending a signal. A beam of light or a radio wave, both traveling at the speed of light. You send your message today, in the year 2026. That message would arrive at the other end of the Orion Arm in approximately the year 12,026. To put that in perspective, 10,000 years from now is as far into the future as the invention of agriculture is in the past. Whatever civilization exists on Earth 10,000 years from now, if any exists at all, would be as different from us as we are from the earliest farmers who first planted seeds in the Fertile Crescent. And only then, 10,000 years later, would your message arrive. If anyone at the other end sent a reply immediately, it would reach you 10,000 years after that. A round-trip communication across the Orion Arm takes 20,000 years. 20,000 years for a simple exchange of information. Not a journey, just a conversation. Just words traveling at the fastest speed the universe permits. This is why the Orion Arm's scale matters. It's not an abstract number on a page. It's a physical reality that defines what is and isn't possible for any civilization living within it. We cannot communicate across the Orion Arm in any meaningful time frame. We cannot travel across it in any conceivable time frame. We cannot even observe the far end of it in real time because the light from those distant regions is already thousands of years old by the time it reaches us. When astronomers study a star-forming region at the far end of the Orion Arm, 4,000 or 5,000 light years away, they're seeing it as it was 4,000 or 5,000 years ago. They're looking at a snapshot from the time of the ancient Egyptians. Whatever is happening there right now, we won't know for another 4,000 or 5,000 years. The Orion Arm is so large that different parts of it exist in different eras of human history as seen from our perspective. The nearby parts show us the recent past. The distant parts show us the ancient past. And none of it shows us the present. Now, let me take this one level further. Because the Orion Arm, enormous as it is just one piece of the Milky Way. And the Milky Way is just one galaxy. We've spent this entire journey talking about a structure that occupies maybe 10% of the galaxy's diameter. The other 90% is out there, filled with other arms, other spurs, other stars, other worlds. The Perseus Arm alone is several times longer than the Orion Arm. The Scutum Centaurus arm may be 6 times longer. The galactic center, with its supermassive black hole and its dense concentration of old stars, is 26,000 light-years away, a distance that light needs 260 centuries to cross. And the Milky Way itself is one galaxy among an estimated 2 trillion in the observable universe. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The Virgo cluster, the nearest major galaxy cluster, is about 54 million light-years away. The observable universe stretches 93 billion light-years from edge to edge. These are distances that make the Orion Arm look like a grain of sand on a beach that stretches to infinity. The scale cascades. It cascades in every direction. Zoom in and you find that even the sun's immediate neighborhood is unreachably vast. Zoom out and you find that the Orion Arm is a sliver of the galaxy, which is a speck in the local group, which is a crumb in the Virgo supercluster, which is an atom in Liniacia, which is a point in the cosmic web, which is a fraction of the observable universe, which may itself be an infinitesimal piece of whatever lies beyond. Every level of the hierarchy is separated from the next by factors of thousands or millions, and at every level, the distances involved are so large that they exceed the capacity of human technology to traverse and often the capacity of human minds to comprehend. This is what the Orion Arm teaches us if we're willing to listen. It teaches us that scale is deceptive, that the labels we put on things, minor spur, local arm, secondary feature, carry emotional weight that doesn't match physical reality. When you call something minor, you create an impression of smallness. But minor in galactic terms means something that's merely thousands of light years across instead of tens of thousands. Minor in galactic terms means a structure containing billions of stars instead of tens of billions. Minor in galactic terms means a region of space so vast that the fastest thing in the universe needs millennia to cross it. These are not human definitions of minor. These are not intuitive definitions. They're technical classifications that exist purely to describe relationships between structures at scales that no human has ever directly experienced. We live our lives at human scale. We walk distances measured in meters. We drive distances measured in kilometers. The farthest most people ever travel is a few thousand kilometers, maybe 10,000 during a long international flight. Our brains evolved to handle these scales. We can picture a kilometer. We can imagine 100 kilometers. We can, with some effort, comprehend the size of the Earth, about 40,000 kilometers around at the equator. But the Orion Arm is 10,000 light years long. A light year is 9.46 trillion kilometers. The Orion Arm's length, converted to kilometers, is a number so large it would take a paragraph just to write out all the zeros. Our brains cannot process it. We hear the number, we acknowledge it intellectually, but we don't feel it. We can't feel it. The neural architecture that handles spatial reasoning in the human brain was built for navigating African savannas, not for comprehending galactic structures. We are fundamentally, biologically, neurologically incapable of truly grasping how large the Orion Arm is, and that's okay. Understanding doesn't require intuition. We don't need to feel the distance viscerally to appreciate what it means. We can use reason, analogy, and careful thought to build a picture that approximates reality even if our instincts can't keep up. That's what science does. It extends human understanding beyond the limits of human intuition. It lets us comprehend things we can't directly experience. It gives us tools to think about scales that our brains were never designed to handle. So here is what you should take away from everything we've explored tonight. The Orion Arm is not small. It is a structure of staggering physical scale, containing billions of stars, thousands of light years of distance, and volumes of space so large they reduce all of human exploration to a rounding error. It is our galactic neighborhood, the region of the Milky Way that contains everything we have ever seen, touched, measured, or imagined. Every star in the night sky is inside it. Every nebula you've ever seen in a photograph is inside it. Every exoplanet we've ever detected is either inside it or visible from within it. The Orion Arm is, for all practical purposes, our entire universe in miniature. Not because there isn't more beyond it, there obviously is, vastly more, but because the Orion Arm alone contains more space, more worlds, and more possibilities than humanity could ever exhaust. It only looks small because the galaxy is monstrous. It only seems insignificant because the major spiral arms are even more monstrous. And those arms only seem manageable on a page because the entire galaxy has been compressed down to a size that fits on a screen or a poster, stripping away the true distances, the true volumes, the true emptiness between the stars. Every galaxy diagram you've ever seen is a beautiful lie. A necessary lie, because you can't draw 100,000 light years at true scale on any medium that humans can see. But a lie nonetheless, one that systematically teaches your brain to underestimate the scale of everything it depicts. The next time you see one of those diagrams, the next time you see the Milky Way drawn in a textbook, or displayed in a documentary with a tiny label that says Orion Arm or local spur, or you are here with a little arrow pointing to a thin bridge between two grander features, remember what that label actually represents. Remember that those few centimeters of ink contain 10,000 light years of space. Remember that inside that sliver are billions of stars, each one a sun, many with their own planets. Some of those planets are rocky, some of them in the habitable zone, some of them may be harboring conditions that could support life. Remember that within that sliver, a structure your eye dismisses in a fraction of a second, there is more distance than humanity could cross in millions of years, and more worlds than we could visit in billions. And remember that you are inside it right now. You are part of the Orion Arm. The atoms in your body were forged in stars that lived and died within this structure. The carbon in your cells, the oxygen in your lungs, the iron in your blood, all of it was synthesized in the cores of stars that existed within the Orion Arm millions or billions of years ago. Those stars exploded and scattered their elements into the interstellar medium, the gas and dust between the stars. Over millions of years, that enriched material drifted and mixed, eventually becoming part of the molecular cloud that collapsed to form the Sun and the solar system about 4.6 billion years ago. You are made of Orion Arm material. You are the Orion Arm, in a very literal sense. A small piece of it that has become conscious and started asking questions about the rest. When you look up at the night sky on a clear, dark night, away from city lights, and you see the Milky Way stretching overhead like a pale river of light, you're seeing the Orion Arm from the inside. That glow, that faint luminous band, is the combined light of billions of stars in our arm and in the arms beyond it, all blurred together by distance into a soft, diffuse glow. You can't pick out the individual stars because there are too many and they're too far away. They merge into a wash of light that has captivated humans for as long as humans have existed. Every culture on Earth has looked at that band of light and wondered what it was. The ancient Greeks thought it was spilled milk from the goddess Hera. Aboriginal Australians saw it as a river in the sky. The Khoisan people of southern Africa believed it was the embers of a campfire scattered across the heavens. The Pawnee people of North America saw it as a pathway for the spirits of the dead. None of them knew they were looking at the interior of a spiral arm in a barred spiral galaxy. None of them knew that the band of light contained billions of suns spread across thousands of light years. None of them knew that they themselves were part of it, made from its matter, bound by its gravity, riding along inside it as it slowly rotated around the galactic center at 230 kilometers per second. But now you know. You know what the Orion Arm is. You know how large it is. You know where it sits in the galaxy and how it compares to the major spiral arms. You know that it contains everything humanity has ever observed or explored. You know that its true scale has been hidden from you by the necessary compression of galaxy diagrams. And you know that even this enormous structure, this 10,000 light-year long bridge of stars and gas and dust and worlds, is just one feature in a galaxy that is 100,000 light years across, which is one galaxy among 2 trillion in the observable universe. The Orion Arm is vast. The galaxy is vaster. The universe is vaster still, and you are here, alive, aware, able to contemplate all of it from a small rocky planet orbiting one yellow star in the inner edge of a structure that diagrams dismiss as minor, but that contains more wonder, more distance, and more possibility than any human mind can fully hold. That is the true scale of the Orion Arm. Not what it looks like on a page, not how it compares to the Perseus Arm or the Scutum Centaurus Arm, not its classification as a spur or a branch or a minor arm. Its true scale is this. It is a region of space so immense that it contains everything we are and everything we know, and it is still just one small piece of something far larger. The galaxy stretches beyond it in every direction, and the universe stretches beyond the galaxy. The scale never stops cascading outward, but you don't need to grasp all of it. You don't need to comprehend every level of the hierarchy at once. Start here. Start with the Orion Arm. Understand that this one structure, the one you live in right now, is 10,000 light years of space filled with billions of stars. Understand that no diagram has ever shown it to you fairly. Understand that it's enormous, genuinely enormous, even though the galaxy makes it look small. And understand that being inside something this vast, being made of its matter, being conscious within its boundaries, is itself a kind of miracle. Not a supernatural miracle, a natural one. The kind that happens when the universe has enough space and enough time and enough raw material for something extraordinary to emerge from something ordinary. The Orion Arm gave us everything. Every star we navigate by, every element in our bodies, every world we've studied, every photon of light that has ever entered a human eye from the night sky. All of it came from here, from this one arm, this one feature, this one neighborhood in a galaxy of neighborhoods. It may be a minor feature by galactic standards, but by every other standard that matters, the Orion Arm is home. And home, no matter how small it looks on a map, is never truly small. So tonight, if the sky is clear and the lights are dim, go outside and look up. Find the Milky Way if you can. That soft, pale band stretching across the darkness. That's the Orion Arm seen from within. That's 10,000 light years of stars and gas and dust and worlds, compressed by distance into a gentle glow that fits across your field of vision. You're seeing billions of suns. You're seeing the interior of a galactic structure so large that light itself needs millennia to traverse it. And you're standing on a tiny planet orbiting one of those suns, looking out at the rest of your arm, your neighborhood, your home in the galaxy. It's vast beyond comprehension. It's beautiful beyond words, and it belongs to you in the deepest possible sense. Because you are made of it, you are inside it, and you are the part of it that learned to look up and wonder what it was. Thank you for joining me on this journey tonight. If you found this exploration meaningful, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember what you've learned. The Orion Arm is not small. It only looks that way because the galaxy is incomprehensibly large. The next time you see a diagram with a tiny label marking our position, you'll know the truth. Those few centimeters contain everything. Good night, and may you never look at the night sky the same way again.